A true Klein bottle cannot exist in our three-dimensional universe without intersecting itself. This topological anomaly destroys its capacity to enclose a distinct interior volume. Topologically, it is a closed, non-orientable surface of Euler characteristic 0. It represents a two-dimensional manifold that possesses no boundary lines. In 3 dimensions, the Jordan-Brouwer separation theorem dictates that any closed embedded surface must divide space into 2 distinct regions, an inside and an outside. Because the Klein bottle is non-orientable, it can only be immersed, not embedded, in 3-dimensional space. It fails to separate the ambient space into an interior and exterior. Commercial glass models are mere 3-dimensional projections. They require a physical hole where the neck penetrates the wall, creating a continuous boundary that violates the true topology. To understand how higher dimensions eliminate intersections, consider a 1-dimensional line trying to cross itself within a flat 2-dimensional plane. By lifting one segment of the line into the 3rd dimension, the self-intersection vanishes completely. The line passes cleanly over itself from an overhead perspective. A 2-dimensional observer, confined to the plane, would see a point appear, split, and merge, unable to perceive the spatial leap that prevents a collision. Non-orientability begins with the Mobius strip. Take a rectangular strip of space, apply a single half twist, and join the ends together. This surface has only one side and one continuous boundary component. Tracing a path along the center rotates your orientation vector by 180 degrees. A Klein bottle can be constructed by gluing 2 Mobius strips together along their single continuous boundaries. This operation cannot be completed in 3 dimensions. As the edges match up, the bodies of the strips must pass through each other to complete the mathematical gluing, forcing a self-intersection in 3 dimensions. Mathematicians represent this structure using a fundamental polygon, a square where opposite horizontal edges match in direction, but vertical edges match in reverse directions. Rolling the square to match the horizontal edges creates a standard cylinder. The remaining top and bottom circles must now be joined in reverse alignment. To match the opposing arrows on the circular ends, one end must loop back and enter the side of the cylinder from the inside. 4-dimensional space provides a 4th perpendicular coordinate axis. We define this extra dimension as W, extending perpendicular to length, width, and height. When the tube approaches the outer wall in 4 dimensions, it alters its position along the W-axis, rendering it spatially separate from the wall. Just as an automobile highway overpass allows cars to cross without a physical collision, the 4th dimension allows the manifold to cross itself seamlessly. With the self-intersection eliminated via the W-axis, the Klein bottle becomes smoothly embedded. It forms a continuous manifold with no tearing and no holes. In 3 dimensions, the intersection line requires a physical opening for the material to pass through. This opening connects the apparent inside directly to the outside. Even if the intersection were mathematically sealed without a hole, a fluid moving along the surface would travel to the other side without crossing an edge. Because there is only one global side, the concept of containing or trapping a substance inside the bottle is topologically meaningless in 3 dimensions. In a true 4-dimensional embedding, the Klein bottle does not divide 4-dimensional space into an inside and outside, maintaining its one-sided nature. Physical glass models exploit gravity and air pressure to trap liquid. They function as complex barometric siphons rather than true topological containers. Liquid remains inside only because the narrow neck prevents air from entering simultaneously, a mechanical phenomenon entirely unrelated to the underlying topology of the manifold. Every point on a Klein bottle is locally identical to a flat 2-dimensional Euclidean disk. The exotic global structure emerges purely from its global connectivity. Parallel transporting a right-handed coordinate frame around certain closed loops on the surface returns it to its origin as a left-handed coordinate frame. This chirality inversion proves the global absence of an orientation covering, a property shared by all non-orientable surfaces, regardless of embedding dimensions.
Contrast this with a standard torus, which is orientable. A torus requires only 3 dimensions to embed perfectly without self-intersection or orientation reversal. The algebraic signature of the Klein bottle is captured by its fundamental group, defined by 2 generators, where one reverses the orientation of the other. Cutting a Klein bottle precisely down its longitudinal axis of symmetry results in a single, continuous Mobius strip, twice the length of the original. Alternative cutting planes can divide the immersion into 2 distinct mirrored Mobius strips, revealing the intrinsic dual Mobius architecture of the manifold. When we project the 4-dimensional embedding back into 3 dimensions, the self-intersection reappears as a mathematical artifact of the dimensional reduction. Topology determines the permissible quantum states in certain condensed matter systems, where non-orientable configurations describe topological insulators and exotic defect lines. In theoretical physics, higher dimensional spaces are compactified on complex manifolds. Non-orientable surfaces serve as vital building blocks for string theory configurations. An n-dimensional non-orientable manifold generally requires 2 n-dimensions to embed smoothly without self-intersection, placing the 2-dimensional Klein bottle firmly in 4-dimensional space. The Whitney embedding theorem states that any smooth n-dimensional manifold can be smoothly embedded in a 2 n-dimensional Euclidean space, guaranteeing that 4 dimensions suffice for our surface. An immersion is a local embedding where the differential is everywhere injective. The 3-dimensional Klein bottle is a global immersion because it fails global injectivity at the intersection loop. In 3 dimensions, the self-intersection set forms a closed curve. Along this curve, 2 distinct patches of the manifold occupy identical coordinates in 3-dimensional coordinate space. Moving to 4 dimensions resolves this singularity. The self-intersection curve separates into 2 non-intersecting spatial curves, separated by a non-zero distance along the 4th spatial axis. Algebraic topology uses homology groups to classify spaces. The first homology group of the Klein bottle contains a torsion subgroup, reflecting its non-orientable, twisted nature. Because the first integral cohomology group reveals the presence of torsion, the manifold cannot support a top-level volume form, meaning it lacks an intrinsic invariant interior volume. Integrating the total Gaussian curvature over the Klein bottle yields 0, matching its Euler characteristic. This topological invariant remains unchanged, regardless of the embedding dimension. Any physical attempt to manufacture a true Klein bottle out of standard matter is fundamentally limited by 3-dimensional space, forcing structural compromises like joints or holes. Ultimately, understanding the Klein bottle forces us to abandon our reliance on physical 3-dimensional models. True topological analysis reveals a seamless, continuous, boundaryless universe, achievable only when we unlock the geometric freedom of the 4th dimension.